Hello, my name is Sekiyama, Division of Materials Physics, Graduate School of Engineering Science, Osaka University, Japan. In this movie, after a brief review of the previous lecture movie concerning the basics of many-electron systems, I explained general formulation of photoemission spectroscopy in solid, including the photoexcitation process in second quantization. Then, I focus on the core-level photoemission. After discussing the many-electron Hamiltonian of the ion in solid, I showed several examples of the core-level photoemission spectra in which the core-level shift, exchange splitting, spin-orbit splitting, and asymmetric peak structures are observed. In the explanations, sometimes I refer also to the previously shared movie entitled as Principle of Photoemission Spectroscopy as an Optical Process. For your learning, please see also that movie. Please enjoy these movies. I start from Hamiltonian of electron in a crystalline solid. There are so many electrons in solid. So there are many electrons are occupied even in one side, where the effect of the Coulomb interaction represented by the E square over Rij are not negligible at all. I explained one electron wave function of the hydrogen-like atom. We can represent one electron wave function as a product of the eigenfunction psi and spin wave function sigma. Sigma is alpha or beta. So since the electrons are fermions, the many-electron wave function must be antisymmetric with respect to the exchange, as like this one. We use the Slater determinant expressed as this determinant. This determinant satisfies this antisymmetric nature of the fermion many-body wave function. The total energy can be divided into this part and this part. So this one represents a Coulomb integral. But to fully understand the electron-electron interaction, another term is required. I introduce exchange interaction by using the lithium atom. After the calculation, we can notice this term is given. This is due to the nature of the Slater determinant. This term is not given by the classical framework. Then I expanded this concept to Coulomb and exchange integral in the general z-electron system. When we consider the many-electron state by using the single Slater determinant, we can define the one electron energy level for the state lambda L like this one. The problem is how to solve each one electron wave function from the given condition. We obtain the information of the wave function of each state lambda I. Then we can express the total z-electron state by using the Slater determinant. So far, I have explained the Slater determinant for z-electron system. In order to describe this state from the vacuum state, I introduce the creation operator of electron as a lambda I dagger as this one. We can also consider its conjugate, the annihilation operator of the electron, as a lambda I. This is usually known as an anti-commutation relation, expressed as this formula. Therefore, we get this relation irrespective of the occupied state or unoccupied state. So this term gives the occupation number of electron. The sum of this operator and this operator becomes 0. This is the same for the creation operator. Therefore, this relation must be satisfied. So compared with this one and this one, finally we get this relation. This is an anti-commutation relation. Then, by using the second quantization, we consider the Hamiltonian of the many-body electron by using the second quantization. We can also express electron Hamiltonian by using the second quantization and annihilation and creation operators like this one. The next problem is how the photoexcitation process is expressed by using the second quantization. This state I and F are state of the electron Hamiltonian, many-electron system. On the other hand, this operation is for the one-electron problem. Therefore, we consider the one-electron wave function to be excited, this one. It should be noted that state lambda j is occupied in the initial state. And we consider the photoelectron wave function phi kf. This is in continuum state, no longer in the bound state. Then the transition probability is defined by using this and this wave function, and we can determine the so-called matrix element of the transition probability MFJ as this formula. It should be noted that within the dipole transition, this term is proportional to this one. In this process, this is the same as annihilation of the occupied state lambda j and creation of another state, unoccupied state kf. Therefore, the photoexcitation process can be expressed by using the annihilation operator A lambda j and creation operator A kf dagger in second quantization. So this MFJ is called as a transition matrix element. By using this notation, we can describe the photoemission process in second quantization. Then I explain the description of the N-electron system in the initial and final state of photoemission. Here the initial state is expressed by using this formula. This is assumption. Here we consider the single Slater determinant for simplicity. The state lambda stands for the bound state for each electron. Here we consider the ground state, therefore the state lambda 1 to state lambda large n to be occupied state, and lambda n plus 1, lambda n plus 2, and lambda infinity stand for the unoccupied state. But this state is the bound state. Here we consider the ion, therefore the energy is negative. On the other hand, this continuum state, Kf, its energy is positive. This is no longer bound to nucleus. Therefore, this excited state is transferred to the photoelectron, which can be emitted and detected in vacuum. For the final state, this final state is equivalent to the annihilation of the occupied state lambda j and creation of the continuum state Kf. In the rigorous sense, we need to multiply this factor, but the result is not affected by this factor because we need to consider the self-square. So important thing is this state is occupied. And by using the sudden approximation, for this state there is no interaction between this electron and remaining or rest n-1 electrons, because electron energy is much higher for this state than this state. Therefore, we do not need to consider the Coulomb interaction between these bands for considering the formulation of photoemission. This is so-called sudden approximation. Then we can divide N-electron space into the bound N-1 electron subspace and photoelectron subspace as this formulation. This is owing to the sudden approximation. As I explained before, the number of electrons of the occupied state is N-1. For the initial state, it is described like this one. So when we divide it into the bound state and photoelectron subspace, for the initial state, for this subspace, the vacuum state in the initial state. Of course, the number of electrons in the bound state is large N. In the initial state, number of electrons is large N. This is an eigenstate of the Hamiltonian He with a total energy of large EI. I defined the corresponding state as this formulation. Then, therefore, this state is equivalent to the direct product of this state and vacuum state of the photoelectron subspace. By using the same notation, we can define the N-1 electron state as this formulation. Then the photoelectron final state is described by using this formulation, the direct product of the N-1 state, bound state, and the photoelectron state as this. Then we can obtain the matrix element like this one. This is just simply put the final state to here and the initial state here and express the photoexcitation process by using the second quantization as this one. Then we can divide to the photoemission process and the bound electron state as this one. Of course, this term becomes 1 because this process stands for the creation of the photoelectron with Kf. The result is this one. Therefore, this term becomes 1. Therefore, this formulation is also expressed as this formula. Here, the MFJ stands for the matrix element of the photoexcitation process, described as this formulation. Then we can understand the general formulation of the photoemission spectra. Here we neglect the effect in step 2 and step 3 in the 3-step model. This is travel to the sample surface, and step 3 stands for the emission into vacuum. Then the photoemission spectral function is given by using this energy omega defined as Ek star minus h nu. Ek star means in the case of solid, the energy from the flame level, and in the case of ion, the same as Ek measured from the vacuum level as this one. We need to sum all over the initial state and final state. Therefore, this kind of summation is required. And we defined energy omega as this formula, so we can understand this one is the same as this one. Sorry, this is large scale is correct. Anyway, the initial state total energy is EIN, and adding the 1 photon energy h nu, that is equal to the photoelectron kinetic energy and n-1 total energies. Viewing this formulation, we can understand that all effects of the optical process are included in this term, MFJ, matrix element term. There is no information about the photon in the other parts. Further, when we assume that transition matrix element MFJ do not depend on the energy and state to be excited, then this matrix element can be regarded as constant. Therefore, for such a situation, the photoemission spectral function is given by this formula. By seeing this one equivalent to the one particle retarded Green's function, here we do not need to consider what happened in the photoexcitation because all effects are included in this term. So this formulation is one electron photoemission spectra, but we do not care about the optical process in photoemission spectroscopy. Sometimes this is convenient, especially for the theoretician, but sometimes it's too simplified. So sometimes the transition matrix element, including the polarization dependence or something like that, becomes a problem, or this term has an advantage in obtaining the detailed information except for the one particle Green's function. But simplification of the formulation of the photoemission spectra, we do not care about the specific experimental configuration for the general spectral function. Then I revisit the electron Hamiltonian for the single site to obtain the co-level photoemission spectrum. This Hamiltonian stands for the many-body electron system, but on the single site. In the single site, all N-electrons are divided into the atomic-like inner core electrons with a number of large Nc and valence electron with a number of Nv. Of course, when we consider the single site, valence state should also be written as a discrete level, but this is a situation that we consider the one site or single site in solid, crystalline solid. Then the valence band state is rather continuum. Anyway, when we divide it into the core level and valence band, we can rewrite the single site Hamiltonian as this formulation. The first term stands for the one electron level for the core level, and second term stands for the Coulomb and exchange interaction, Coulomb and exchange energy between the core electron. For instance, this one and this one. And third term stands for the Coulomb and exchange energy between the valence and core electron. For instance, this one and this one. And this term stands for the one electron valence band energy without considering any Coulomb and exchange interaction. And this term stands for the Coulomb and exchange energy between the valence band electron, like this one. Then the first two terms represent only core level. Therefore, we can summarize these two terms as Hc. That means Hamiltonian for core electrons. And we can also redefine the non-interacting valence band electron energy. That means interacting with the inner core electron in the site. This is realistic. Then we can rewrite total electron Hamiltonian as this formula. Here we redefine the valence electron energy with considering the interaction between the inner core electron as this one. The third term stands for the Coulomb interaction between the valence electrons, this one. So here, this term is included in advance in the second term. This is okay for the initial state, but in the core level photoemission in the final state, the one hole is created in the core level. For such a situation, we need to add this term. So this is 1 minus NC, therefore this term becomes 0 in the initial state, because all core levels are occupied. In the final state, one state is excited, then that is equivalent to the situation that the core hole is created in the final state. Then this term becomes active. Okay? So this is finite value for the number of valence electron is larger than 0, and one core hole is created. Then we can redefine the Hamiltonian for the valence electron by summarizing these two terms. Then we can rewrite the total electron Hamiltonian as a summation of the core electron and valence electrons and interaction between the valence band and core hole. Core level electrons Coulomb interaction is included in advance in this term. So then we can understand that for the valence band photoemission process, there is no core hole in the final state, because even for the final state, this term becomes 0. In such a case, there is no change between the initial and the final state for the HC term and third term. In such a situation, only we consider the second term, the Hamiltonian for the valence band electron. On the other hand, for the core level photoemission process, interaction effect between the inner core and valence electron must be considered due to this term. Here we assume that this electron is excited, labeled as C. Then the final state, N-1 energy, is expressed by using this formula. We suppose that here we create the hole in this state, then due to this term, Coulomb interaction is switched on between this electron and this core hole. Then this energy is reflected in the core level photoemission spectrum. I said that we can understand the valence band electronic structure by using the core level photoemission, that is due to the presence of this term. Then I can discuss the core level shift reflecting the different valence state by using the core level photoemission. This is a formulation of the photoemission spectroscopy. And here, omega is the energy difference between the initial state and the final state. On the other hand, the residual N-1 electron energy is expressed by using this formula. So the peak energy should be described by this formula. From this formulation, we can notice that peak binding energy is a minus of omega and this one. So it should be noted that this state is negative and therefore the sign is split. Okay? So the peak binding energy is always positive for the occupied state. And therefore this state is much deeper binding energy. And this term is always positive because the Coulomb energy is much larger than the exchange energy. Then the high valence. High valence means, for instance, the silicon 4 plus is higher than the 2 plus or something like that. But high valence state means less valence electrons. Therefore, the energy of this term becomes smaller. That means the peak binding energy is higher for the higher valence state. So this is a real example of the core-level photoemission spectra. Silicon 1s photoemission spectra of ytterbium kappa 2 silicon 2. You can notice that there are two peaks labeled as A and B. Peak B is relatively stronger, for the photon energy becomes lowered. And peak B is located at the higher binding energy side of the peak A. From this result, we can consider this situation. Silicon 1s peak binding energy is of the order of this one. Therefore, the photoelectron kinetic energy at the photon energy of 2.5 kilo-electron volt, the mean free path is of the order of 10 angstrom or something like that. And here, in the electron kinetic energy dependence of the mean free path. But for the excitation energy of 6 kilo-electron volt, photoelectron kinetic energy is larger than the 4 kilo-electron volt. The resultant mean free path becomes longer. And it is also known that when we measure the oxygen 1s photoemission spectra at 4 kilo-electron volt, we see some oxygen 1s spectral weight. Therefore, we can conclude that peak A is coming from the bulk silicon side in the ytterbium kappa 2 silicon 2, and peak B is coming from the surface oxidized by the oxygen. So the silicon O2-like state in the surface. These spectra, photoenergy dependent spectra, can be understood as a consequence of the different mean free paths as a function of the photoelectron kinetic energy and the different valence state. This is a rather neutral silicon, and this is oxidized silicon 4 plus or something like that. This is due to the different number of the silicon valence electrons. So this is a story of the chemical shift in the core-level photoemission. This logic can be utilized in analyzing the core-level photoemission spectra. I would like to introduce another thing, the exchange splitting in the S core-level photoemission spectra of the magnetic side. So this is a core-level 3s photoemission spectra of the chromium dioxide. From this composition, we can notice that chromium is 4 plus state with nominal electron configuration as 3d2. As I explained later, for the s-orbital there is no spin-orbit interaction. Therefore, usually the s core-level spectra should be single peak, but we see the two-peak structure in the chromium 3s binding energy area. It should be noted that accidentally overlapping of the other core level is not seen because 3p level is located around here and there is no oxygen core level peak around here. So therefore, we need to consider another thing other than the spin-orbit coupling. It is known that this is exchange splitting, reflecting the final state energy due to the 3s3d exchange integral. As I said before, the peak binding energy is calculated by using this formula. But in this case, the difference is seen in this term. Namely, if this core electron is excited, downspin excitation, no exchange interaction between the 3D electrons. On the other hand, if the upspin electron is excited, in the initial state, the exchange interaction is active for originally this electron. Therefore, the final state energy is different between these two configurations, and energy split is about 4 electron volts. Therefore, this exchange energy is half of this splitting, namely around 2 electron volts. So this two-peak feature indicates the signature of the magnetic ion of the chromium side. But this is an interatomic effect. We cannot discriminate the ferromagnetic or antiferromagnetic. Anyway, J means the exchange energy depends on the overlap between the valence and inner core orbital. So this is a 3s3d exchange energy where the principal quantum number is the same. So of course a similar exchange is acting on the deeper core level, for instance 2s3d and 1s3d. But for this state, the overlap becomes smaller and smaller to the 3D state. Therefore, the energy itself becomes lower and lower. So in reality, we cannot detect this splitting. This splitting is so small compared with 1s energy width. Therefore, in order to see the exchange effect, usually we see the s-orbital photoemission with the same principal quantum number. I would like to show the effect of the spin-orbit interaction. And this is also the single-site effect. So this is a Hamiltonian of the spin-orbit interaction within the scalar relativistic formulation. And in this case, the quantum number L and spin quantum number S is no longer good quantum number. But the sum of these quantum number representing the total angular momentum is still good quantum number. Therefore, when the spin-orbit interactions are switched on in the core level, the core level split into the L plus 1/2 and L minus 1/2 with this degeneracy. So I'd like to show the real example of the photoemission spectra. This is a simple photoemission spectra of gold in this binding energy range. So this is a 5s spectra, and this is a 4f peak, and this is 5p peak. You can notice that the 5s peak is a single peak and no splitting. But for the 4f and 5p core-level state, the two-peak structure is seen. This is due to the spin-orbit coupling. For instance, for the 5p state, 1 electron orbital quantum number L is 1, and for the 4f state, L is 3. It is known that in the core level photoemission spectra, the spin-orbit splitting in the core level is clearly seen, like this one. Okay? So this is an explanation how to read or how to obtain the information from the core level photoemission spectrum. I briefly explained the asymmetric core-level photoemission peak structure for metals, which are rather independent on the electron correlation effect. When we measure the core-level photoemission spectra of metallic materials, so-called asymmetric peak structures are seen, as shown in this figure. These figures show the real experimental data of the core-level photoemission spectra of cerium, palladium, tin. So upper panel shows the spectrum of tin 3D 5/2 while the lower panel data showed a palladium 3D core-level photoemission spectra. This black dashed line indicates the symmetrized line shape of the lower binding energy structure. So you can notice that asymmetric structure is seen like this. This line shape is expressed by this formula, where the so-called electron hole pair is created, which are located at the film level. Situation is like this. When the core level electrons are excited, at the same time, this kind of excitation can be created. So this is an electron hole pair in the vicinity of the film level. The number of the electron hole pair is unknown, but there are many possibilities, one pair or two pair, three pair or something like that. So such a situation is described by this formula. Alpha stands for the asymmetric factor. When alpha is 0, the peak is symmetric. While alpha is near 1, the peak structure is so asymmetric. This xi indicates the so-called cutoff energy, which is comparable to the bandwidth of the valence band. Of course, some portion of the event of the core level excitation, there is no creation of the electron hole pair. Kinetic energy of such electron is located at like this, which holds the energy conservation law of the photoemission spectroscopy. But this electron kinetic energy is lower because some energies are used for the creation of the electron hole pair in the vicinity of the film level. In order to see this phenomenon, there must be finite number of the electrons crossing the film level on the excited side. Therefore, these results tell us that both palladium and tin valence band electrons cross the film level. In other words, both the tin and palladium valence band electrons contribute to the metallic behavior. So that is the explanation of the asymmetric core level photoemission spectral peak for metallic material.